Now I want to, this is something that I had indicated in my first tutorial. Now I want to make it precise, the connection between the quiver theory and orbit closure of the determinant. Basically all, in one line, all Newton degenerations as I defined in the first tutorial of semi-invariants of these quivers would be sitting on the orbit closure of the determinant. And when the things are tame, you can expect kind of polynomial time theory of Edmonds, but when the things are wild, things can go wild, and that is what causes the complexity of the orbit closure of the determinant to shoot up. And so as I had indicated, so I just want to make that. So that was one gap in the first tutorial, so I just want to fix it. So recall let Z be a symbolic determinant of size m equals polynomial n over x1 So by symbolic determinant we mean that it just some matrix of size you have m equal to polynomial n by matrix where each entry is any combination of the very linear form of x1 to xn, and then you take determinant of z and you express it as monomials in z alpha. So let's say c alpha and z alpha, whether these are the monomials in x alpha. Okay. And then you define the Newton of z.
Power alpha?
Yeah. X alpha means just monomials. And yeah, you can take some indices here, okay? Yeah. And then the Newton of z, by that we just mean the Newton polytope of z. So you just take all these exponents and take the convex hull, and given any phase inside the Newton of z, so you define the Newton degeneration with respect to that phase, Newton degeneration. So between determinant we denote it like this: if z will be equal to c alpha x alpha, and you just range alpha over the things that occur in the phase. Okay.
C is a matrix whose entries are linear forms in the X's. Is that?
Yeah, and fixed linear forms.
Any linear form.
Yeah, but fixed. You fix it. You're not varying.
Fixed linear forms.
Yeah.
Right.
As in the permanent versus determinant, a similar thing. Okay. And
Polytope of Z is what?
So
Is of the determinant
coefficient is non-zero.
or of all the entries or of just of the determinant?
of the determinant, Newton polytope of z,
Of Z or the determinant?
you just take the exponents where c alphas are non-zero.
That's the Newton polytope of the determinant.
Yes.
Of
He
Z.
expands. Expands the area.
The polynomial that computes, I think.
Yeah.
It's not the determinant of Z. If Z has linear forms in the x's, then it comes out as a crazy polynomial in the x's. And you just take the monomials that you see.
Occur.
Well, so the thing is, Z is both a matrix and then a polynomial in the notation.
Yeah. I'm just. I should have written Newton of det z, etc. If you want that. Okay.
Yeah.
And Newton degeneration is for any phase in the Newton polytope, not necessarily facet. You just choose those alphas which occur in F, and you just truncate it there. Okay. And the point is that this occurs in the orbit closure of the determinant m that we saw, because you can just whatever. Okay, so it occurs, and the question now is, when does determinant f have a small size? Okay, question is, when does determinant fz have a small size, small circuit, that is a circuit of polynomial size? Okay, that is the question. And the conjecture was not always, and there was a complexity theoretic reason for that, because complexity theoretic reason were that first of all, that given z and alpha, deciding if x alpha occurs in determinant z is hard, very hard actually, as hard as, so I won't go into this, as hard as deciding if the determinant of if the permanent of a given matrix is equal to some fixed value given in binary, very hard, as hard as computing the permanent basically it says. And two, here membership problem for the Newton polytope of Z is also hard, is P hard, which means given any rational point, deciding whether it is in that Newton polytope is a hard problem, okay, in general.
Just a naive question. So the number, the space of such, how does that compare in size with the space of?
Space of what? Space of what?
Space of F's and space of small circuits.
What do you mean by space of F? You mean this cardinality of this? Yeah, so in general,
The choices of F versus the number of small, whatever small.
yeah, so the choice of F, so generally what you would want is that if this is hard, what this says is that this would kind of behave kind of randomly, and now you have to choose F's so that the number of alphas in that is exponential, okay? I mean, you can choose F so that it has exponentially many vertices, and there, if this kind of things go randomly, the circuit size would shoot up. That is the intuition. Yeah.
So here you want to take a codimension one phase or some?
No, any phase. Yeah. But you should have exponentially many vertices on it. Okay?
Expectation on the other.
Yeah. So the thing. So for example, so the problem is, you want some specific families where you would detect the problem. Okay, so this problem is construct some specific z's. Okay, construct specific z's, and that we want to construct using quiver theory. For which this kind of behavior which complexity theory suggests should occur, for which determinant Fz does not have a small circuit for all phases of the Newton polytope. Okay, and it would be basically the semi-invariants of wild quivers what Jerzy was talking about. So now let me say the Q is a quiver without oriented cycles. And you can have possibly involutions also here. I mean, though he didn't talk about it, you can have involutions and then you have similar theory. Okay, and then given dimension vector, vectors alpha and beta, and any representation V of the quiver with dimension vector alpha with dimension vector alpha. So let CV, okay, be the semi-invariant in what he denoted as SI of QB. Okay, so the semi-invariant of that. Okay, so which is basically this is by definition the ring of. So if you take all the representation space of representations with a dimension vector B, C, and then you take the whatever SL QB, take the GL action on that, and yeah, so you can identify that with SL QB kind of the space at least. Yeah. So this is the semi-invariant, and now with this basically we so let let we denote Q be the total number of nodes and arrows in the graph, the total size of the graph, and you let alpha equal to summation alpha I and beta equal to summation beta I, the total size of the dimension alpha vectors. Then notice that from the definition that he gave, that CV is which to make it precise, we will also denote sometimes by CV Q alpha B beta is a symbolic determinant. The symbolic determinant of size that is polynomial in the size of the quiver and the sizes of the dimension vector.
We're just going to fix one quiver once and for all.
Yeah, right now.
So,
Yeah.
so let's take the one with six
Arrows, right.
nodes and one preferred. All the others have arrows going into it.
Let's say 3. Just take the same.
Okay.
Good enough. This is a bad quiver already.
Okay, fine.
Okay. Okay. So now what you can do is with this quiver, you can of course denote a subclass of VP associated with this fixed quiver, and it would be basically, so this basically is the set of all of.
So how is this quiver connected with this polytope?
No, now this symbolic determinant would basically be the symbolic determinant coming from that CV, okay? In the construction of CV, he constructed that determinant, right? Yeah, so that is that Z going to be now, okay? Okay, so the set of symbolic determinant families of the form. So basically you just take all of this kind, the symbolic determinant families of the form Q, alpha, beta, okay? So this would have the number of variables here, okay? So the number of variables here, number of variables will be equal to basically the dimension of the representation space QB, so which would be less than total beta square, okay? So you would want that Q plus alpha plus beta is less than some fixed polynomial in N, as you do in the complexity class definition of VP, some fixed polynomial. And you also want that Q and beta square is less than or equal to N, so that the number of variables is more than what is required to describe the matrices in that. Okay, so that gives you some family of this thing, and so that is
The side of Q now, side of Q
is the number of arrows and number of rows and arrows and everything.
These degenerations, these are all still in the Valiant world? Or?
Yeah, they would all be.
Still in Valiant.
Now you're all in Valiant world because all these are symbolic determinants, okay? And then you define the Newton degeneration of this to be basically, then you take all these Newton degenerations. They won't be in the Valiant world anymore. They would be in the orbit closure, okay? So if you take the Newton degeneration of VP, then they would be inside VP bar, okay? You're taking orbit closures, okay? Because all these Newton degeneration belong to the orbit closure of the determinant. And so now the question is, in complexity theoretic question is, when is Newton PPQ inside VP? Okay, when do you live in the Valiant world and when you live outside? Okay, based on the quiver. That is the question, and the conjecture would be that if and only if, and you are always assuming that Q is without oriented cycles, and this is required for some reasons, technical reasons I won't go into, without oriented cycles, okay? Conjecture would be if and only if Q is tame. Yeah, finite is considered tame, whatever. Yeah. Oh, yeah.
That's why we're down to a dichotomy.
Or finite, depending upon how you define tame. I mean, some people think of finite as the domestic or something. There is some tamest or domestic also. I mean, they have all kinds of weird terminology. So okay. So let me take the simplest example. So the simplest tame quiver would correspond to what I would say was the origin of actually the complexity class P. Okay, and to prove that, essentially would require generalizing Edmonds theory to all tame quivers, which is already would be quite a, I think, important thing. And the thing is, basically what the conjecture is saying that Edmonds theory won't generalize to wild quivers, but to tame quivers it would. Okay, so that is basically what what it is saying. Okay, so take the simplest case, tame case. So take Q to be one thing with this involution. Okay, so if you don't take involution, then the generator is just the determinant of x, which is short, and if you have this involution, then the generator would be the square root of, so you take the matrix where you have Zij here and minus Zij. Okay, so this is the skew symmetric matrix, and its square root is what is called the Pfaffian. That would generate the same invariant ring in this case. Now, so in this case, the Newton polytope of square root of det z is precisely the perfect matching polytope. Perfect matching polytope of the complete graph on whatever, there are 2n nodes. Okay, yeah, it is exactly the perfect matching polytope of the complete graph on 2n nodes. And for this Edmonds, and so this is actually an important thing about complexity theory, which I think this is some jewel of complexity theory, and in fact it was the origin, so I wanted to convey this to mathematicians. This is what needs to be now generalized to arbitrary tame quivers. So Edmonds, this is the fundamental result of Edmonds. First, that Newton Z in that case, okay, is defined by zero Zij less than or equal to 1. Then you have for all I, you have that Zij, you sum over j is equal to 1. This is kind of obvious, you would say obvious constraints, because it's a perfect matching polytope. It just says that every edge 0 or 1. Here it says that for every vertex you would have at least one thing going. But what is not obvious is this third constraint, is that for any odd subset T of 2n, so if you take all edges which belong to the co-boundary of T, that is, if you are taking, this is your 2n nodes, and if you take any odd subset, then basically some edge, okay, in the matching has to come out. Okay, so basically it says that this Zij is greater than or equal to 1, and using this, so there are exponentially many such constraints. And the amazing thing is that he actually showed that the membership question is in P, okay, and this actually is the birth of, in some sense, okay, and using that,
Despite there being that many facets.
it has exponentially many facets.
Yes, despite that membership.
Yeah, that is a miracle, okay, and that is in some sense the first non-trivial, and using that, then of course he also gave a polynomial time algorithm for finding minimum width perfect matching in a graph, and that is actually in some sense the beginning of P, theory of P. Okay.
So what's the idea that you can use membership?
No, it's not. It's a non-trivial algorithm, highly non-trivial algorithm.
Highly non-trivial. This is the beginning of complexity theory. Okay, I mean this is a.
Before P was defined.
Yeah, but but he defined. So actually he motivated. This is why complexity class P is so important. So this actually, and the membership problem for Newton Z belongs to P, okay? And now what Kiao has shown is that in that case the Newton degeneration, so this is theorem Kiao, and this is basically because it has some kind of miraculous description, that in that case it would follow that determinant of Fz has a small circuit for every F in the Newton polytope, okay? And it actually crucially depends on these Edmonds kinds of constraints. So the point is, if you have constraints very special so that the membership problem is easy, then you can kind of expect membership problem is easy, and in that case this problem is also easy. Deciding a monomial occurs in it is just basically deciding if alpha corresponds to a perfect matching, which is easy, okay? So if these two basic questions associated with the Newton polytope are easy, then you can kind of expect Edmonds theory. So the problem here would be, so basically what the conjecture says is that this, so the main problem here is,
Then just the membership problem for the polytope is easier to prove than for the matching. Or am I? Yeah. Well, just to clarify, I mean,
the membership problem is non-trivial. I mean, first of all, you require that description, and then you get the.
polytope is like the convex combinations of the perfect matchings.
Yeah.
But the 0, 1 vector situation is first.
No. It doesn't have to be 0, 1. Could be any rational point.
Can be any rational point.
Yeah. And this is actually the basic oracle. Like if you see on all this, if you look at the ellipsoid algorithm for constructing minimum weight perfect matching, this is the basic oracle that you would use in the ellipsoid algorithm. So this is really the heart of the matter in some sense. This is why everything connected with this is in actually P, because of membership, and also it gives you a separating hyperplane and all that.
Don't directly check these exponentially many, but if constraints. But if one fails, you can find, if not all of them are satisfied, it is possible to efficiently find one.
One. That is the whole point, okay? So you have to have that kind of structure to it. Then if you have that kind of structure, then Kiao tells you that actually determinant F has a small size for everything because of that specific structure. But in general, such a structure is not going to be there. So
make sure that the Kiao theorem is a theorem in algebraic complexity. It's about arithmetic circuits, whereas the Edmonds theorem is in Boolean complexity. It's about,
but it is the heart of the proof.
Just pointing out that there is a difference between the two types of.
Yeah, actually, and there is this small circuit right now. We can't actually, given F, you can't actually find the small circuit efficiently because it's actually the problem of de-randomization. Okay, so you are in a loop there, but it exists. Okay, it exists. So the problem is, so I said that. So when you say the conjecture is that the Newton of VPQ is inside VP if and only if Q is finite or tame. So basically what it means is that when Q is finite or tame, you have to actually show, first of all, for example, that the membership problem is easy and so forth. Okay, so that would basically generalize Edmonds theory to any quiver of tame type, which would be very, very interesting. And everybody knows in complexity theory that Edmonds' result was a miracle. I mean, you don't expect such miracles to happen, and when the things are wild, we are not expecting that to happen. And
I should have asked this a while ago. For those of us not in complexity theory, what is Edmonds' result?
This.
That is
The characterization,
and the thing that membership problem for Newton. Huh?
The characterization of the polytope and the polynomial time algorithm to solve the membership problem.
So we expect that would hold for any tame quiver. So I think that is one intermediate thing to work on, and not what does that mean? So the problem is that all of these occur, and so in general they would be so what that means is that you have this orbit closure of the determinant.
Ketan, there is a question.
Yeah.
I'm just wondering if you checked, so Edmonds, that's maybe his first miracle, then he proved, Edmonds proved some other miracles about, we generalize this to matroids, polymatroids, where also there is a polynomial time algorithm for something. Do these come from quivers also?
Maybe. I think that I think is worth checking, okay?
Absolutely.
Okay, so the other, I think Avi has made a point. So the Edmonds and Loas also, I think Loas actually have generalized this to various kinds of matroids. So the thing is, do they correspond to any kind of quivers, and then try to generalize that matching theory to arbitrary time quivers. So that is the thing.
And there is also another part to this, which I think Edmonds mentions in it. That's a theorem of Tat.
Yeah.
Which gives you a characterization of. So I mean, it's pretty. I agree. It's a pretty amazing paper. It gives you. It actually shows. So Tat had previously shown, if you want, that matching is in coil P.
Yeah.
Gave you a sufficient condition, easily checkable. So how does this reflect in this general picture? So perhaps what I'm asking is, perhaps it's easier to start before you develop this whole.
To do that.
To ask.
Yeah.
To seek a Tat type.
Theorem for time quivers.
this
Yeah.
area.
Time quivers. Yeah.
So you know how to.
No, I don't know. That's why I'm asking you. So I don't know, but I believe that that's a reasonable. Now, what does it mean?
I'll say one more word, because the Tat theorem, I will not say the details, but it's fairly easy to state. And the proof is also not very difficult. That it asks what happens if you throw away a number of vertices in the graph, and the graph splits, how many of the connected components are even and how many are odds. That's the only condition that you're looking at.
So I think, I don't know, have you seen any such things studied in quiver theory or whatever?
Maybe not in Cooper's, but I think Harm Dirksen has some papers on invariance of matroids and so on and so on.
No, I'm asking, Tat theorem is earlier to that.
Yeah.
So it says, let me say it, it's not so complicated. A graph is a perfect matching if and only if there is. So the only type of obstruction to a perfect matching is that you can throw away, let's say, some number L vertices, and there are more than L connected components of odd order. That's an if and only if description.
But these are just theorems about graphs, right? Here we are talking about representations, so it's kind of very.
No, I mean, they should be, but it would take some, I mean, I think the thing has not been studied and there is much to be done here. I mean,
So in some sense, this is really something, I mean, in hindsight, we understand that that's something on the way
to understand, yeah?
So perhaps it's an easier place to
Start. I mean, if we don't understand domestic animals, we are not going to understand wild animals, okay? I mean, this is actually the simplest tame and finite type, okay? The domestic case, okay? So what I'm saying is, what this says that all these wild guys are actually occurring here, okay? And this is why actually the NNL currently is in X space, okay? So this is why the complexity of NNL currently is so high. And as I said, that the positive thing is that in spite of all these wild things sitting on the thing, so the positive thing, so the negative thing is that all these wild things are sitting on the orbit closure of the determinant. Because of that, there is an exponential blow up in the circuit sizes. Because of that, this problem NNL. So the negative thing is that NNL for this delta det m is currently in X space. And we don't know how to get it to even X because of these problems. Because of this, basically. So in complexity theory, we simply have no idea of how to get X, right now there are exponential size circuits, so you have to just cycle through all of them, and that requires X space. You can do cycling through by Grobner-Massey's theory and all that, but we don't know anything better than that right now. But the positive thing is that if the GCT1 conjecture is true, then ignoring quasi-factor, NNL belongs to quasi-det. So it can come down from X space to det, which is a huge thing, which is basically the difficulty of the problem right now. And that is way beyond. So I think some open problems first that we should work on. First, this tame quivers. Try to Edmond's theory here. I think that would already give us some understanding. Then second, I said was that equivalence problem and NNL for V mod G arbitrary without any restriction on the dimension of G belongs to P. That would be the second intermediate problem. And the third problem is the Kronecker problem belongs to P. I think if we understand these three problems on the way in this program, we have made a lot of progress. I mean, we are still very far from understanding the orbit closure of the determinant, but there is already a lot on our plate before we can really hope to understand all that. So I think with that, let me stop, and now we can have discussion on what to do next and so forth. Yeah.
So when this was billed as an open session, I foolishly thought we were going to spend time discussing open questions. I mean, so there's three. Maybe people could suggest some more.
Yeah.
I'd be very interested.
Okay. Yeah.
So, I wasn't sure what the format of this would be, so I didn't really.
No, I mean now.
But let me, so with the possibility of writing obviously correct things, I want to talk about two things which already came up. So one is the point I keep repeating to any audience like this, I mean many of you are anyway doing it, is that maybe it looks more and more like the determinant is hard and we should understand simpler objects and simpler polynomials. And if you think from the point of view of computational complexity theory, we cannot even prove lower bounds for things that look like this. And we have products of linear forms. Well, these are fine. As far as we know, it's possible that determinant M, or even permanent M, is much more outrageous than determinant of permanent itself. It's possible that you can embed them with, with just n things here where n is poly M. So as far as we know, you can compute determinant and permanent just by a formula of polynomial size of depth 3, which looks like this and just has affine forms in the variable. It's outrageous, and we should prove that that's impossible. So we don't know how to. So let me give you an easier problem. An easier problem follows from the fact that the elementary symmetric polynomials in n variables. So I basically want you to study these guys as opposed to the determinant. The orbit closure of these guys.
What is it exactly? You want to study orbit closure of under what?
Under
GLA?
affine, well, AN. Under affine subgroup, because I have to allow. So it turns out that it's, these are polynomials which look complicated. They have exponentially many monomials, but nevertheless, there is a very simple formula like this. It's a very simple formula just with n and n. So despite the fact that this is complicated polynomial, I can show you this very beautiful result of the norm. Anyway, it's a fact. So, what? I can show you. But let me just, but because of that, an even easier question to ask is, you are answering him, Joseph, are you answering him?
Yeah, it's kind of
I can answer everybody.
Okay, so it's one of those. Okay.
I can just let me finish the sentence, then I can show you. Because this can be done. An even easier question to ask is, can you embed determinant or permanent for your favorite polynomial, not into this, but just into the symmetric polynomial of linear form. So can you write that M as the symmetric, the elementary symmetric polynomial for some K and N polynomial in M of some linear forms in this variable. So this is an M by M matrix, which has variables, I don't know, Y and J. So this will be
And what kind of
the Y.
what kind of lower bounds for n and k would make you happy?
Super polynomial. Super polynomial.
So you cannot do it for n and k polynomials in M. That would be done.
Yeah, well, k is less than n, so you cannot do it for n, which is polynomial.
So these are affine?
Affine forms. It's very important that they are affine. Joseph talks about the method of partial derivatives, which is the baby version of everything that Kayal was doing, something that Noam Nissan and I did long ago. You can use it to show that if you restrict yourself to homogeneous linear form without constants, then there is an exponential lower bound on embedding even determinant into this term. There's an exponential lower bound. But once you allow constants, and now I'll answer your question because you see the power of constants, you can get polynomial size formulas for this elementary symmetric polynomials. Not for determinant, maybe, I don't know, but definitely for. So, just want to say that this is just a question of whether the determinant is contained in the determinant M is contained in the action of the affine group on acting on the symmetric polynomial without talking generality with symmetric polynomial. So we just, we want to understand whether you can. It's the same kind of question we keep asking. I mean, the whole week we were asking about determinant. It's a much simpler polynomial, the elementary symmetric polynomial. And I think
maybe the orbit closure of that doesn't contain any nasty stuff.
Yeah. So it's a great question whether your conjecture about the orbit closure
won't solve for it. I mean,
So you expect, so here's a great conjecture, which in fact I was going to suggest. Show that this closure does not have any wild stuff. For elementary symmetric all the things in the closure of small circuits. I think it makes sense. I didn't try. I don't think it will be easy, but I think it's much more doable than for the determinant. So I'm suggesting this.
May I ask the notation? Does n mean?
Yeah, n is polynomial in. So you want to show this.
And what is n? What kind of group?
Oh no, this is just a fine group. So you.
Fine group.
Translation.
Translation.
I see. So you just. Well, this is the way I like to express it. Just write it as a symmetric function of affine forms.
An elementary symmetric function.
Elementary symmetric function. One of the elementary symmetric functions. With no loss of generality takes the minimum.
I think the other similar thing is that for diagonal tape-tree circuits, which geometers know about, it does not contain points with blow up in the circuit size.
Yeah, I should have mentioned that even simpler objects than elementary symmetric polynomials are just a diagonal sum of powers.
Yeah.
And for that we have lower.
No, but on the boundary.
On the boundary, I don't know. Actually, yeah, that's it. Yeah. So, yeah. Start from the most.
We know that there are no net points?
He's the one.
So may we rephrase your question about characters of GL? So they seem sure polynomials when the Young diagram has only rows and the determinant has only one column. No, it is this. Okay.
Yeah. For me, it's less natural, but maybe for you, it's more natural to think about it this way. Anyway, yeah. So there are simple polynomials to study and to study the closure and so on. Now, for those who want to see this is sort of real magic. but it's very simple. So here's the circuit. It comes from the fact that you all know that if I take some values, I have my variables x1 through xn, I want one of the elementary symmetric polynomials in it, I'll compute them all, in fact. So I take some variable t, and I look at this product, t plus x1,
Generate function.
t plus xn, this is just simply the sum of the symmetric. Okay, and then here we have whatever t put in, and minus, right? So this is in the xi. That's obvious, but that's great. This is the circuit. You see the circuit. So the multiplication gates. I'll tell you what the addition gates. So we'll have n plus 1 multiplication gate. All will look like this. So here it will do, let's say, we take, this will be responsible for t equals 0. I'm going to do interpolation. So here I go simply x1.
Oh, I see that.
x1.
That's how you're going to recover the
xn. Here I multiply 1 plus x1, 1 plus xn. And here I multiply n plus. I need the field to be larger than n. So I just evaluate this for different values of t. Now what do I put here? Well, if I have all these values, I have evaluations of this at n plus 1 points. For any fixed k, I can tell you what, there is some constant here.
Okay, that's
it.
fine.
Right?
Okay.
So it's an n squared size formula for the symmetry.
Yeah, but I don't understand. You ask us to express the determinant as a symmetric polynomial in linear forms, and you just said above that that's hard.
Yeah, no, so what I'm saying, this is the way to do the symmetric, elementary symmetric ones. And I want you to show that nothing like this could work.
Oh, I see. This should be an
impossibility. Yeah.
I understand.
Yeah, we
That's
don't
the point. Yeah, it's too simple.
Now, you can notice that, the linear forms here have just two, are of size 2. So you can start, like we always start, with easier problems and try to say, well, maybe maybe if there are 2 or 3 or constant, it cannot be done. And Niraj has a new result showing that if this is small, let's say constant, this requires exponential size. But this exponential lower bound breaks down when the finite grows. I don't want to say it exactly. Anyway, that was one thing I wanted to ask. Just study these simpler reductions to simpler polynomials. The other thing I mentioned during Joseph's talk, so I'm not going to write anything down, I'll just say it again. All the low bound methods which succeeded for some classes of circuits have a common framework. The common framework is that we take, just write one line. All the ones that were successful, and also many of the ones that Joseph described that are being attempted by various people, all these young flattenings and all these other things. They have the same form. They take, if we take, I don't know, p with n variables and degree d. So these are all polynomials. All polynomials in n variables, homogeneous of degree d. I know you like S0, but it doesn't matter. Anyway, we have this space, and we take a linear mapping from this to some vectors, whatever we want. So this is a linear mapping. And the way we prove lower bounds is let's say for for polynomial p, we want to say that the dimension of L of p is bigger than the dimension of anything trying to compute it. It can be a family of circuits, it can be the closure of determinant under, it's just a set of, so it's bigger than the dimension of L of Q, of course, Q in some class Q, which is what we are trying prove the log. That's how they work. I think it's a great question. So partial derivatives like this, and shifted ones are like the shifted partial derivatives, and the projected shifted partial derivatives are like that, and the Young flattenings are like that. And it's,
So this is upper semi-continuity that the dimension of the image can only drop.
No, not necessarily. Not necessarily, but that's how the proofs work.
Generation.
This is
Under
bigger.
generation, the dimension of the image can only drop.
Yeah. Right. But anyway, you are trying to do something like this, and one question I don't know the answer to. I think it's a great question. I think the feeling I have, and maybe Joseph shares the same feeling, is that linear maps may not be enough. So it's it would be a great question to say that no matter what linear, you just study it in complete generality. No matter what linear maps you cannot use it to separate permanent from determinant.
But if you have a nonlinear map with that dimension, you look at the tangent space.
Exactly.
I mean,
So excuse me, if you have a nonlinear map with that property, then if you look at the tangent space,
You get a linear map.
you then get a linear map.
yes.
So why would nonlinear be better than?
Or even nonlinear map can be completely changed into linear map by going to symmetric power.
Yeah.
Well, but I think
some-
what's hidden in what Avi didn't say is that there's this determinantal property that
Yeah, that's why that has to be
it's
made
that it's-
precise.
Yeah, you're right, because
amounts to computing a
otherwise you can
determinant
do
with
this
linear
many
entries.
Yeah, you need to limit the families. The families you allow, but I mean, that's the family tools that all polynomial size formulas or just translations of determinant of small size of polynomial size. Then so you can study it specifically. Here is a specific question. I didn't think about, so maybe I'm not stating it right, but something like that. Does there exist an L for which the dimension of L of the permanent, or you need actually the padded permanent? The padded permanent is bigger than the dimension of anything, any cube in whatever. How does it, that's how you know. And so in the Orbit closure of the determinants on n variables or n polynomial. Is there any map which will distinguish? I don't know. I mean, that's a concrete question. And this here, I think that it's not the same question to move to, if I replace it by some polynomial map. It's not, anyway, I don't know what it would even mean. It's a polynomial map, and it would not be a vector space, but your map goes wrong. Anyway.
So it's probably true that you can always distinguish with some linear maps, because if you have any object, you can always construct some linear maps.
Yes, that is.
But not
let me
maybe not just by the dimension.
Yeah, I should say, I didn't like, what this map, we have some fixed vector space, and what we are mapping is to subspaces outside now. We are mapping polynomials to subspaces of this vector. That's what happens in all this.
I understand, because it's a family of vectors.
Yeah, exactly. So, and that's a concrete question. Maybe it's not precisely formulated, but I would love to know whether.
But the way that works is that's sort of continuous map of polynomials.
Yeah.
There's a lower semi-continuity dimension.
So do you have some
And that's what you're
specific
taking
L in
advantage of.
mind
But
which
can't
might
you
be
linearize
good?
something that might-
No, I wonder whether there is any.
Can't look at this- look at all
I don't know.
tangent
Maybe
space.
there is no evidence. Maybe there is. I mean, I don't know, but I find it very interesting.
No.
What's the limit? I mean, we have
There'd be points which are
complexity
very
some.
Which is essentially good for both maps, I guess.
We are very, how do you say, reflective or science in that when we fail to prove something, we try to look for the reason, namely prove that all the methods we use so far fail. There is a history of such things, and some of you have heard of natural proofs and relativization and various things like this. So this would be, maybe this is not this technique in general, no matter what kind of, algebraic geometric intuition you have, it will, linear is not enough. I don't know. I think I put more time than any of you wanted to take, so.
Thank you very much.
So, any comments or questions?
Well, I was going to mention a question of Ketan's, because
Yeah.
I think I can say it for algebraic geometers. So it's too bad because Ray Leckerman will be here, but he's not here at the moment. This is really a question for him. So there's this variety of Veronese. Which is just the d powers. And then you have this symmetric order rank, which is the smallest r, or the wearing rank of P, the smallest, so P polynomial. It's the smallest r such that P is some x1 to the d plus to the d. So this is, let's call that r, and then we have r under bar, smallest r such that P is a limit of things like this. So these are things of rank, at most, rank r. These are things of rank, order rank r. And the question is how different can these two numbers be? So does there exist a sequence J where the growth of Pj is greater than a polynomial in the growth of the order rank? And the conjecture is no.
These two ranks should coincide.
No, they do not coincide in general.
Then what do you think?
So the order rank can, so if I look at the polynomial x squared, x to the d minus 1y, that has order rank equal to 2, and rank equal to, what is it, d minus 1 or d over 2, something like that.
D is D.
What?
D.
D. I knew it was something like that. So here you have 2 and d, so they could be very different, but still d grows like a polynomial.
A polynomial in 2?
All right, so I have to make the question more precise.
Yeah. So because the
I think it is polynomially d in the number of variables.
Yeah, so polynomial
in d in number of variables. Or whatever.
No, but it has to be made precise, though.
Yeah, no, I agree. It should be made precise.
Yeah.
So, yeah, so let's...
Otherwise, the answer is true.
Exactly.
Yeah, so let's see. So we have n, the number of variables, and d, but let's just set n equal to d without any loss of generality, so we only have one parameter to worry about. And so what we want is a big gap between these two that grows faster than the polynomial. So r of pj minus r of pj greater than
You want difference? That doesn't sound good.
A fixed D, yes?
Ratio, that's what I meant. Yeah. I'm getting there.
What's the
Another month and I'll have it said precisely.
what's the I mean how fast do these rings grow again?
It's completely unknown. The only thing that
No,
is
not the quotient. I mean the bigger one. But
the bigger
what's
one,
the maximum rank?
the maximum rank is known to be at most twice the maximum border rank. So,
Yes.
but of course the maximum border rank can grow exponentially fast in n. So you want to, so if there's going to be a counterexample, it's going to be something of smallish order rank, where the rank is close to maximal. That's the idea.
So what's the maximum rank? Where's that?
I told you, the only thing that's known is it's at most twice the maximal border rank, and the maximal border rank is this, n plus d minus 1 choose d, divided by what? And
but you want the minimum border rank and the maximum rank.
I understand what that is.
You want the minimum border rank and the maximum rank.
Yeah.
Right. The ratio to be maximized. And can that grow very fast?
Okay.
That's Ketan's question. He believes no. I think that's reasonable. And I think this is a very clean question in algebraic geometry that we could work on.
So I have a question about this Kp and P. I mean, that's motivated in part by your result on Little-Richardson coefficients, but is there any other reason besides just hope for that?
That NNL is in P.
The Kp, no, Kp is in P.
Yeah, but the intuition comes from
The previous one.
Yeah. My intuition. I mean, not the Little-Richardson coefficient. There's a big gap between Little-Richardson.
Yes.
On that result. NNL for delta Z is in P if whatever the complexity theory conjecture.
Okay.
And this is actually in some sense easier form of that because here you have to battle with all the horror on the border and all that.
Okay.
And if this is not easy, then I think that this won't be easy, and if that is not easy in this way.
I couldn't hear it. That's the conversation.
You couldn't hear? Okay. So what I'm saying is that if this is not in P, it's very unlikely that this is in P. And then,
Okay.
all the things that I talked about, which none of us want to happen, would happen, and I think that none of those things would happen.
There's like in this talk, like it's covered like a very big field in complexity, which is the polynomial and edge testing with randomization. And it's like in fact there is a theorem which not formally but which shows if you know how to make polynomial identity testing or how to make the randomization, you can separate permanent from determinant. It's not completely formal, and I want like to note one very nice problem in the randomization. So the problem is the following. Assume that you have a polynomial p of x in p of x1, x2, so on, till xn, and I want to find one concrete polynomial which is not identically zero on any subspace of dimension, say, 10. What's the minimal degree of this polynomial can we find? So
You have a polynomial which is
I want to find polynomial in n variables. So such that for every vector space of dimension, say, 10, p of x1 to xn restricted to v is not identically zero. This, in my opinion, it's a very clean question. Like dimension, so making dimension argument, one can show that there exists such polynomial. One can show that exists such polynomial of degree n to the 1 over 10.
What does he mean?
He doesn't need it. He just says it exists.
Exists.
So once you get up there, a generic polynomial will have that property.
Yes, generic polynomial will have this property. Now, like, what?
degree.
Yes, degree.
This one with the degree is that side.
Yes. Degree of inside. You can say exactly what's the meaning.
Order of, no, I can't read. Order n to the power 1 by 10.
Yes.
Yes. So, I'm saying that dimension arguments say that generic polynomial has this property that
Explicitly degree polynomial.
But what happened with the symmetric, elementary symmetric polynomial of degree 11?
it will be 0. I can show
For
that
what?
on some subspace.
Really?
Yes. Like, it's maybe not trivial to find subspace, but like you can show if degree is too small, like if degree is less than
No,
and
just above your dimension, one above your dimension.
No, he says n to the 1/10. No?
I know, but I'm giving an even lower,
Much
cheaper.
better.
Well, if it's slower, you can show that there is not a, I can show proof. And the reason it's actually dimension argument because if you work over complex numbers, you can show that there is not exist such polynomial. And so this polynomial degree
Exercise
approximately
in Harris's.
1/10 this property. And like reason why you need such degrees, because if you look say on P of lambda 1 V plus lambda 2 V lambda 10 V, you expand it as polynomial in lambdas. You get here some polynomial with I1 plus I2 plus I10 equals to D of lambda to the power I. Here will be some polynomials Pi. You'll expand it this way, and it's 0 if and only if all these polynomials are 0 at some point. Like it's V1. But it's 0 if all these polynomials you can find like some points in V1, V2, V10, such that all these polynomials will be 0. So you cannot take it's too small. But we can find such polynomial like we can show that for generic polynomial this degree will have this property. And it looks very clean question. And it will have like many implications, like in generalization of polynomial density, for error correcting codes, like, and it's like there are many other questions which just.
I see. So for if dimension was not 10 but 1, you would take the moment.
Yes, then dimension 1 you can solve it, and for dimension 2 you can also solve it, not more. Maybe I have other questions.
But if you,
from the
okay, so I mean this should, if it happens, if there's some degree where it happens, then that should happen for general polynomial of that degree, because you could.
It's happened for it's true for generic polynomial. But the question is to find like explicit one. To find one and to prove for this one that it's not 0.
Okay, I see. I see. Not to find the lowest degree where this can occur. But
No, it's very again in a haystack.
Yeah. Okay. Sure.
I really like it.
So what, Carlo?
That's a great one.
That's a great one.
What?
So what does it mean?
What's mean explicit? So it's a question that was discussed many times, and in any sense that it's so. Let's say find any polynomial, but don't say generic polynomial. Generic polynomial is not explicit. Dimension argument is not allowed. Dimension or random arguments are not allowed.
So, but the number of coefficients is exponential.
Yes, but it's okay. It's okay. So show like there is many ways for like there is an algorithm which writes coefficient of each monomial in polynomial time.
But I think many people use. I think in shallow depth circuit they think explicit if it is in sharp fit. Is that what it is?
It's
Like
in
permanent
P to write. It's in P to write down the coefficient. Every coefficient.
Yes, that is uniform BNP.
Yeah, uniform BNP.
Uniform BNP. That is what.
Yeah.
Correct. Exactly.
So the coefficients can be exponentially large or something.
No, coefficient you can write down efficiently.
You have to write down coefficient efficiently. So I will not allow you to make tricks like taking coefficients like irrational numbers or So no cheating like this, like or taking coefficients which are E or.
Why don't you just say uniform uniform VNP? I think they would.
Like permanent.
Yes.
Permanent has exponentially many monomials, but it's not a problem to know what it is.
Have you tried asking Nathan, because he gave a talk about Nathan, who gave a talk about Fano schemes in hypersurfaces. And this is a question when
Okay, this is why I'm asking this question now, because I don't know.
Nathan left today morning.
But his co-author's right in front of you, I believe.
Yes, sorry. Because this is a question, yes, for finding a hypersurface with empty Fano scheme.
But write one down that has an empty Fano scheme.
Thing with an empty Fano scheme is,
But
Still, I would
following your idea, if there's some, there could be some interesting, linear section or manipulation one could do to the permanent to kill its Fano scheme, that would be a way to take their paper as a starting point. You look at where those Fano schemes come from because they know where they come from in some cases for the permanent, and then you try to kill those off one by altering the permanent. That would be one strategy.
So I don't know precise results, but in the morning, Nathan told me that Fano schemes of hypersurfaces are static.
Oh yeah, well,
yes.
Well known that you can
Those people that.
make integers which are large, exponential large, behave by some high argument like generic complex numbers. Right? So
Yeah.
but you don't allow this kind of.
No.
Yeah, that's the sort of problem.
You need some.
So what is the model? I mean, coefficients.
should be some small.
Can you compute it in polynomial time? Why don't you-
Yes, so you can. So let's say for every monomial.
With height.
Every monomial.
Having this conversation all week long.
And alpha like
Accurate,
efficient.
No, the other order of quantifier, there is an efficient algorithm which is when given the description of alpha.
Yeah, because whenever
I realize.
Efficient algorithm such that it's alpha and gives
But efficient in what model?
efficient to say polynomial. So look, find
Polynomial in the index of the
You
location.
just notice that the description of alpha is just a sequence of integers, right? So the input is just a sequence of integers, the exponent. And what, so this algorithm, the normal model, your favorite computer program. Any computer program that takes integers and produces, let's say it's a 0-1 polynomial, then insists on a 0. We'll just say 0.
But the Fermat surface, the Fermat surface,
Yeah, it can add, multiply as long as it's polynomial time.
plus x, m to the some m.
No. You count
x2 to the m.
No, it's
plus
not
x to the m. Fermat surface.
It's a bit model. You count down. Yeah.
I don't think it's for master. I think I checked it, and for this specific polynomial it doesn't work. But I don't remember what's exact surface were at 0.
Yeah, you said then I would just say a few words as a chair.
Yes, well, it's time to end this conference, I think, so we had a very intense week, and I would like to thank all the participants for sharing.
And as the chair of the GCT workshop committee, on behalf of the committee, I would like to thank all the speakers for the great talks, for all the participants for their enthusiasm, for making this workshop a success. Thank you.
And maybe we should thank the organizers for the great job.